Hello friends, Eli Hibbett here with the Pwn Your Homework Physics Series podcast. If you're looking to prepare, review, or gain an added edge or point of view about topics in physics, then look no further. Tune in each week to unlock your understanding of the physical world surrounding us. And now let's dive right in. Alright, how is everybody feeling today? I'm your host Eli Hibbett, here with episode 10 of the Pwn Your Homework Physics Series podcast. I'm really excited. 10 episodes is a kind of a milestone, so I'm excited. I hope you're doing well. I hope you're kicking butt in the physics world. And so first thing, this podcast is late. I feel bad. I'm trying to really stick to my Tuesday schedule, but this week a couple things got in the way. I am at a hotel in Detroit with terrible internet without going too deep into it, and I'm trying my darndest to get this thing going. But I had a real great influx of ideas of things that I kind of wanted to include in the show, so it's actually kind of a good thing that it is a little bit late, but I'm going to try to stick to getting to next Tuesday, kind of staying on my schedule. So one thing I wanted to introduce is a new segment where I kind of take the topic of the episode. This episode is going to be physical constants, and I'm going to inject a clip of a popular song from somewhere. And if you know what it is, you can leave a comment on pwnyourhw.blogspot.com. Drop me an email at info@2718productions.com or tweet me at 2718productions. And the first person that gets a hold of me and lets me know what the song is, I will give you I'll give you something cool. Maybe I can hook you up with a free code to download on my apps or something like that if you are a iPhone user. We'll figure something out. So it's not always going to be directly related to what we're doing, but the lyrics will kind of maybe hint at what we're getting at. So without further ado, here is the first clip.
All the strangers look like family. All the family look so strange. The only constant I am sure of is this accelerating rate of change.
So I wonder how that's related to what we're going to talk about today. So if you know who wrote that song or what live DVD that's off of, bonus points, drop me a line at pwnyourhomework.blogspot.com. So with that, I'd like to get into our inspirational quote of the day. And again, Carl Sagan's showing his face. The simplest thought, like the concept of the number one, has an elaborate logical underpinning. The brain has its own language for testing the structure and consistency of the world. So the reason I chose that quote is because I think that the notion of the number one kind of shows that there are these underlying numbers that kind of crop up in the world around us all the time, and they seem to be almost embedded in nature, and they're not real nice numbers like 1, or they're not really round numbers. They're these weird numbers like 3.14 or 2.718281828 or 3 times 10 to the 8th, although some of them, like 3 times 10 to the 8th, are kind of based on our measurement system, but there are other ones like the golden ratio, pi, e, stuff like that are just kind of hanging out in there. And why those numbers exist, or why we're going to get into some of the the mass of the electron and the mass of the proton, why those are those numbers. If they were off by even a little bit, if electric charge was a little different than it was, the whole universe would be entirely different. So the electron and proton wouldn't be able to form an atom together. It's almost certain that life wouldn't form, or at least not life as we know it, but it would be a very different ball of wax. So it's kind of interesting that these numbers kind of propagate and that they interact the way they do. Okay, I think we're going to have to let non-tired Eli grab the reins here. So that was recorded last night and about 3 o'clock in the morning, and I had just put in a monster day at work, and I was very, very tired, but I had felt so terrible about the fact that I'm really trying to maintain this schedule that I tried to push the envelope a little bit and try to barrel through, power through, and crank out the episode. Not in a bad way, not like I just want to get this out there, but I was excited about it. I've been thinking about it all day. It was kind of distracting me from what I was doing, and the notion that I had a terrible internet, and I just wanted to make sure that I stay consistent with this was so important to me that I tried to horse it a little bit. And I think you could tell, I mean, that dude sounds tired. And for the intro, I actually kind of like the intro. I think he's kind of a funny guy to listen to. But when we're getting into the meat and potatoes of this podcast here, where we're talking about physical constants, 13 must-know physical constants, I think that we should have a little more energized Eli to guide you and take your hand through this journey. So, but that guy's funny. I like him. So, if you're tuning into this podcast today, the day it's airing, or 10 months from now, right now, when I'm recording it, we're in the month of October, and so I'm trying to get into a little bit of a spooky Halloween type vibe with the podcast, so I decided to come up with 13 must-know constants. I mean, if that isn't so scary, I don't know what it is. 13. But these are really important constants. You should know them, you should know the symbol, you should know what they mean, you should know the value, you should know what they are, and when you see them on paper, you should not only not be intimidated by them, but when you see that constant, you say, okay, I know what that is, I know that that's a constant, it's not a variable, I don't have to solve for it, it's a given, it's a known in the problem, and it's one less thing for me to worry about. And I can even write it off the top of my head, I know what it is. So, these 13, get to know them. Alright, here we go. So the first constant is c, the speed of light, at 3 times 10 to the 8th meters per second. It's what was known as the cosmic speed limit. Nothing that we know of can go faster than it, at least not yet. Hopefully we'll discover something that can go faster than it, we can break this barrier down, but right now we don't know anything that travels faster than the speed of light. And it has the symbol c, and if you've ever heard of a little equation called E equals mc squared, that is what the c represents, is the speed of light squared. So E is equal to energy times the mass of an object times the speed of light squared, saying that if you took all the mass and converted it into energy, it would be related by the constant speed of light squared. So that's a doozy. I think everyone in the world knows E equals mc squared. So that is the speed of light c. You're going to see it all over the place, so you should know that one. Next, we have a little group of constants here, which are kind of like attractive forces, I guess, let's say. So we have little g, which is 9.81 meters per second squared, which is the acceleration due to gravity on Earth. Nowhere else in the universe is the acceleration due to gravity 9.81 unless you have something that's exactly the same size as Earth. And the reason that is because the attractive force of gravity is related to the mass of the Earth. So when you're on Mars or when you're on the moon, you notice that the astronauts can jump a lot easier. That's because they have much less gravity. The force of gravity is much less. And so that varies throughout the universe. But since we all live on Earth, most of our physical problems come with Earth as a reference. So 9.8 meters per second squared. You should definitely know that one. Big G is 6.67 times 10 to the 11th Newton meter squared per kilogram squared. And what that is the gravitational constant, which is universal. If you take any two masses in the universe and you want to know the attractive force between them by gravity, the force is equal to g m1 m2 divided by r squared. So r being the distance between them, and the masses m1 and m2. So this is one of the first topics that anybody dives into in an introductory physics course. So you're going to see this constant for sure. So get to know it, and you don't really want to have to look it up because you're going to be doing a million problems with g in it. Big G, 6.67 times 10 to the 11th. And the next constant that I wanted to kind of go through here is what is known as the Coulomb force constant, which is Ke, but it's also represented by 1 over 4 pi epsilon naught, which has two other constants, which we're going to get into in a couple of seconds here. But the reason that it's kind of related to this gravitational constant is when you have two charges, the force between them is described by F, the force is equal to K, Q1, Q2 over R squared, which is almost identical to the other equation we just talked about, which is g m1 m2 over r squared. So this attractive force by gravity is very similar to the attractive force by charge. So since they're so similar, they tend to be introduced together. So you'll be doing a lot of problems with these as well. So K sub E, 1 over 4 pi epsilon naught. Get to know it. This next little grouping of constants is what is known as rest masses. And so we have three what are called fundamental particles: electron, proton, and neutron. And so the rest mass of an electron is 9.11 times 10 to the minus 31 kilograms. And we usually designate that in problems as m sub e. When we want to talk about the rest mass of a proton, we use 1.67 times 10 to the minus 27 kilograms. And if we're talking about the mass of a neutron, we also have 1.67 times 10 to the minus 27 kilograms. But, I mean, protons and electrons make up everything in the visible universe. So I think they're deserving of knowing what they weigh, I would say. So you're also going to be doing a gazillion problems where you have to pull it off the top of your head. So mass of an electron, 9.1 times 10 to the minus 31 kilograms. You should be able to say it that fast at the drop of a hat. You should never have to tell anybody, oh, I need to look that up. But if you do, I have a tool for you, which I'll tell you about later. But first, let's press onward and get through these last three little groupings here. The next one I'm going to deal with is charge. The first one, we want to know the fundamental charge, which is the charge of an electron, which is 1.6 times 10 to the minus 19th coulombs. And that is generally expressed as just the letter E. It's usually italicized, and you'll use that a lot in the attractive force problems where you're dealing with charges. The next constant, the EV, which is an electron volt, which is also a unit of measure, is 1.6 times 10 to the minus 19th joules. But what it is the amount of energy required to move an electron across a potential difference of 1 volt. And so what we have is a volt, 1 volt, times the elementary charges we just talked about, 1.6 times 10 to the minus 19th coulombs, and we get 1.6 times 10 to the minus 19th joules. So that is an electron volt. And when you're dealing with these very small quantities where you have 10 to the minus 19th joules, it doesn't really make any sense to use exponents that small. So we use this unit EV, and everybody knows what it is, and it makes a lot of sense because it's in terms of elementary charges. And so you're going to see it a lot, EV. Our next little group of constants here are related to photons. And so a photon is an electromagnetic wave, which means it has an electric component and it has a magnetic component. And these actually propagate as waves, but they're perpendicular to each other. So if you have one wave moving in the vertical direction, let's call that the electric wave, then the magnetic wave will be moving in the horizontal direction. And so when a wave is moving through an object, we always kind of consider that object to be some deviation from a vacuum or free space. And so when a photon is moving through a vacuum, the electric component is governed by what's known as the electric permeability of free space, which is also known by the symbol epsilon naught, which is 8.85 times 10 to the minus 12 farad per meter. And the magnetic component of the photon is governed by the magnetic permeability in free space, which is 4 pi times 10 to the minus 7th Tesla meter per ampere, which sounds like a very convenient, easy number. Thank you, Mother Nature, for letting us use that one. But they are actually highly relatable, and I will get into that after we finish out these constants here. But it's kind of interesting because before I was talking about the Coulomb force constant, which includes this 1 over 4 pi epsilon naught, which is the same epsilon naught, this 8.85 times 10 to the minus 12th. And we will get into how that's related later on. And so in an intro level course, that's pretty much where you're going to see that epsilon naught showing up all the time. But if you take later courses, or for me, my specialty in grad school is electromagnetics, it's everywhere. And everything in your life, every piece of matter, every light that you see, every photon that touches your eyes is governed by this constant. And so I think it deserves a little bit of respect. And so I think that these might be my favorite two constants of the bunch. I mean, if you had to memorize, let's say 3, I would say memorize the speed of light, memorize gravity, and memorize EV. But when we get into a little later why these two numbers are so important, I think you may come to appreciate a little more why they're my favorites. But let's wrap it up. We have one more little subtopic to go here, and these are irrational numbers, but they're very natural irrational numbers that are found in nature. The first one is pi 3.14, which goes on for millions and millions and millions, actually unending number of decimal places, and it is the ratio between the circumference of a circle and its radius. And since nature tends to favor this circular motion, and so pi is all over the place in nature. And the other irrational number is E, which is 2.7182818828. And that's, since my name's Eli, I named my productions after E. And yeah, so E is a really cool number. And what it is if you have a constant like 1 or 2 to the x power, and you take the derivative of that, is not equal to itself. And anything above e, like 3 or 4 to the x, is not equal to itself. But this 2.718281828 to the x is actually another irrational number which doesn't end. But e to the x, the derivative of e to the x is equal to e to the x, and the integral of e to the x is equal to e to the x, which is very convenient. For whatever reason, Mother Nature loves it, and it is all over the place in mathematics and in physics and in nature. So maybe Mother Nature is trying to make things a little easier for us math-wise, so we don't have to compute such complex derivatives and integrals. But it's a great number, and you should know it, at least to 9 decimal places, because it's so darn easy. 1828, 1828. One of my math professors told me this, and I never forgot it, was that Andrew Jackson was elected president in 1828, and so if you learn 2.7 and then 1828, 1828, you can say that I know e to 9 decimal places, and so you can say 2.7, 1828, 1828. So it's kind of interesting, and it's not a hard number to memorize, and you're going to see it all the time, so you should definitely know it. So yeah, I think that wraps up our 13 spooky constants, and if you want to dive a little deeper, you can check out the show notes at pwnyourhw.blogspot.com, and I also have a free app in the App Store. It's Exploring Physics, Physical Constants, and it goes through these constants in a tap review form and then also a flashcard form where you can review it any way you like, where you can look at the definition and have the constant, have the value. But I like the tap review a lot because when you don't have these on the tip of your tongue, if you want to know, oh, what's the speed of light, C, you can go through the tap review and say, okay, C, tap it, and then you have the value right there. You don't have to go through the anguish of Googling it in our day and age where all that information is right at our fingertips. So, one last thing I'm going to leave you with here, the cliffhanger I was trying to insinuate throughout the show, that why are these numbers mu naught and epsilon naught important in any way, or why are they interesting, is that if you take these two numbers and you calculate 1 over the square root of epsilon naught times mu naught, what you get is the speed of light. And so this cosmic speed limit, where this is the fastest that light can travel in our universe, is governed and actually curtailed by these two constants, the electric permeability and the magnetic permittivity. So when I learned that, that just blew my mind in half, and so I thought I'd share that with you guys, that these constants are connected and they are embedded in our universe and they are part of who we are. So you should learn them, even if you're not going to pursue a career in physics, which I can't imagine that to be the case with anybody, because I mean, even if you're just curious about the world, then you're automatically a physicist. So I think that's going to do it for this week, guys. I hope I'm keeping you excited about physics. Thanks for listening up to episode 10, and I'll see you next week with episode 11. Sorry I'm late, and grab the app, Exploring Physics, Physical Constants. Free! Free! Doesn't cost you a thing! So, I'll talk to you later, guys. Take care.